Greetings. All right, we're going to try to find all relative extrema for this function that involves some trig functions on the interval from negative 2 pi to 2 pi. And let's see how this goes. So whenever we want to find all relative extrema, we first want to find the critical numbers or critical values for the function, which means we need to figure out where the derivative of this function is either 0 or undefined. So we have to go grab our tool of being able to take derivatives and worked it out. So here's the function. We should already know that the derivative of cosine is negative sine of x. So with the negative that's already on this cosine here, we're going to be left with just sine of x. Okay. So the negative times negative sine will give us just sine of x. And then for the second part of the expression here, we have to apply our product rule. And so I'm going to take the derivative of the first factor, sine of x, and the derivative of sine of x is going to be cosine of x, times the second factor, cosine of x. And then I'm going to add to that the derivative of the second factor, which is negative sine of x, derivative of cosine negative sine of x, times the first factor, sine of x. And so we can actually simplify that a little bit. We can do it a lot, but I'm only going to do it just a little bit. So we have our first sine of x, and then we're going to have cosine squared x minus sine squared x. Now, a lot of students, when they see cosine squared of something and sine squared of that same something in a relationship, they automatically think, oh, that equals 1, because of the fundamental Pythagorean identity. Well, it does if I'm adding those two terms together, cosine squared x plus sine squared x equals 1, but here I'm subtracting them, and so this doesn't equal 1. There is, however, a trig identity, the double angle formula for cosine, where you could rewrite this in terms of just, cosine of 2x. But I'm not going to do that because I don't think it helps us in solving this problem. But there's nothing wrong with doing that necessarily. It's just not my preferred way of solving it. So, nonetheless, to get back on track here, here's our first derivative. So I need to figure out where this first derivative is either equal to 0 or undefined. And since all of our trig functions, rather, let me rephrase that, sine and cosine have domains all real numbers. There's no places where this function is undefined. In other words, f prime is defined for all real numbers. So there's no critical numbers found by looking for where this is undefined. I just need to now set this equal to 0 and figure out the values of x to make this equal to 0 within the domain, the restricted domain that they gave us, negative 2 pi to 2 pi. And so the best way to solve a trig equation like this, I shouldn't say the best, but a typical way would be to try to get all of the same trig function involved in this relationship. And here is where I'm going to use that fundamental Pythagorean identity to rewrite this. I'm going to take the cosine squared term and rewrite that as 1 minus sine squared of x from that fundamental Pythagorean identity, so that I get sine of x, and I get plus 1 minus sine squared x minus sine squared x is equal to 0. And then I can combine our like terms here. I'm actually going to do some rearranging here. So I'm going to put the 1 first for a moment. I'm going to put the sine of x in the middle, and then minus 2 sine squared x is equal to 0. Now, personally, I like my leading coefficient of my dominant term to have a positive value. And so my dominant term here is the sine squared term, so I have a negative 2 as its coefficient. I want that as a positive 2. So I'm just going to subtract everything or add whatever is appropriate from both sides. So I get 0 on the left, and then I'll be when I move the negative 2 sine squared x over, I'll have a positive 2 sine squared x minus sine of x minus 1, and of course still equal to 0. And so now we got to figure out how to solve this for x. This is just a quadratic, and hopefully that solving quadratics isn't too challenging for you. If it is, you can talk to me about that. But this is just going to factor rather straightforwardly. I'm sorry, I'm having a little technical difficulty. I'm having a little trouble with my app here for a moment, so I keep grabbing a feature that's not on the screen. But it's going to be a binomial that factors into, or rather a trinomial that factors into two binomials. Since 2 is my leading coefficient, I'm going to have 2 sine of x and sine of x as the first two terms in the binomials, that's the only way I can multiply this back together and get 2 sine squared x, being that 2 is a prime number. I mean, I guess they could both be negative, but that would be unnecessary in the process. The other term the last term, the constant term in our trinomial is 1, and so the last term in each binomial has to be 1 as well, because that's the only way I'm going to get 1, something times something to give you 1 here. So that this works out is going to be 1 times 1. And then remember, the middle term was negative. We had a negative sine of x, so I need that term when I multiply this out to be negative. So I'm going to have to put my negative over here and a positive over here, so that when I multiply this out, and I multiply these two terms together here, I get a negative 2 sine of x, and then I multiply these together, I get a positive sine of x, and together they'll make a negative sine x. But so that's how it factors. And then, of course, by our zero product property, we get 2 sine of x plus 1 is equal to 0. We have to solve that. And then we get sine of x minus 1 also equal to 0. We need to solve that. So we'll get sine of x is equal to negative 1/2 through the magic of algebra. Sine of x equal to 1 over here. Now, we're only looking within the domain negative 2 pi to 2 pi inclusive. And so with this shouldn't be that hard to figure out. So let's start with the second value. When does sine equal 1? Well, if we think about the unit circle, sine of 1, remember sine is the y-coordinate for any point on the unit circle, and so the sine of the measure of the central angle. So with this being 1 right here, how do I get to that point? Well, pi over 2 gets me to that point, okay? That's the only time in one positive rotation around the unit circle. So before, between 0 and 2 pi, it only happens once, and that's at pi over 2. But if I rotate in the opposite direction, I can get there by going negative 3 pi over 2. And since we're on the interval from negative 2 pi to 2 pi, I have to look at rotating clockwise 1 full circle and rotating counterclockwise 1 full circle, and I get those two values as the solution to the second equation. So you get negative 3 pi over 2 and pi over 2 as the two values here. For sine of x equal to positive 1/2, let me go ahead and clear this slide here, and then we have to figure out when sine is negative. We should know that sine is negative in the third and fourth quadrants. Well, that's not my best picture here. And then hopefully from your special right triangles, you know that the reference angle here is going to be pi over 6, because the sine of pi over 6 gives us 1/2. And then we just adjust the angle so that we get to the proper quadrant. So again, each reference angle here is pi over 6. So in other words, if I want to rotate from the positive x-axis from standard position all the way around to here, okay, I have to make a half-circle rotation to this point, which would give me pi, and the rest of the rotation would be pi over 6. So that angle would be pi plus pi over 6, which is going to be 7 pi over 6. And then if I were to rotate from standard position again to the fourth quadrant angle, around to here, excuse the bell in the background, that would be like rotating all the way a full 2 pi, but then subtracting from it pi over 6, so because I didn't quite make it to the full circle. So that gives me 2 pi minus pi over 6, which would be 11 pi over 6. Okay? So there's those answers there. But then I also have to be able to get there rotating clockwise, because if we have negative 2 pi to 0 included in our domain. So then rotating clockwise, I'm going to get negative pi over 6 for this angle right here is one of my answers. And then one more over to here, which would be negative pi minus pi over 6. Actually, that's not true. Negative pi plus pi over 6, which would give me negative 5 pi over 6. I switched angles in my mind. Negative 5 pi over 6. Not my best explanation on that, but those are the 4 angles that we end up with. All right, so let's put these values here. And so we had 7 pi over 6. we had, I'm trying to remember here, 11 pi over 6. Those were the two positive ones that came from one rotation counterclockwise, and then we had negative 5 pi over 6 and negative pi over 6 in the clockwise rotations. Now, at this point here, now that we have 6 critical numbers, we have to make a decision on how we're going to identify where we have any relative extrema. The relative extrema could be at any one of these 6 points, or at all of them, or none of them, but these are the potential locations for the relative extrema. Now, there are 2 tests for determining whether there are relative extrema at a certain location. One of the tests is the first derivative test for relative extrema, which means we would set up intervals from the domain, the restricted domain of this particular example, about these points, and then we would test the first derivative, a value of the first derivative from each of those intervals to see if the first derivative changes sign, positive or negative sign, at any of these points, and then if so, determine which type of extrema it is. Or we can use the second derivative test for relative extrema, which means we would take the second derivative of the function, and then from there we would plug these values into the second derivative and determine, whether we have the graph being concave up or down to determine whether we have a relative max or a relative minimum. And so I'm going to actually do the second derivative test, because with these 6 points, that's a lot of intervals to set up, and I don't think we would need to do all of that. So let's go back over here for a moment. So we had, there was our first derivative, so just getting that in mind, and we'll probably need that later, so that's why I put it there, but we'll come back to it. So f prime of x was sine of x plus cosine squared x minus sine squared x. And so the second derivative would be cosine of x, and then we're going to have plus 2 cosine of x times negative sine of x. And then I'm going to run out of space here, so I'm going to put this down here, minus 2 sine of x times cosine of x. Which is kind of nice, because those 2 terms there are identical to each other, and so we just got to combine them. So we end up with cosine of x minus 4 sine of x cosine of x. And there's actually a double angle formula for sine contained in that pattern there, but it's not needed, so I'm not going to bother with it, but you certainly could rewrite it like that if you'd like. So at this point here, we're going to take all of the different values that we determined were critical numbers and plug them into the second derivative here, and determine whether the output would be positive or negative. So let's take f double prime, and I'm just going to start picking the first the set of solutions from the first equation. So 7 pi over 6 was one of our solutions, and I need to know if this is positive or negative. So 7 pi over 6. This is where this picture was coming into play, because I knew we were going to need this. So this little diagram here reminds us of where sine and cosine are positive when we're in the different quadrants. And where this becomes relevant, because right now 7 pi over 6 is in the third quadrant, so I know the sine of 7 pi over 6 will be negative, and the cosine of 7 pi over 6 will also be negative. So now if I go back over here for a moment, and I think about what the value is going to be here, without calculating it precisely, I just need to know if we get a positive or negative value. So cosine of 7 pi over 6, I'm going to get a negative number here. In fact, let me change the color for a moment. I'm going to get a negative number here, and they got minus. The 4, that doesn't matter so much. The 4 doesn't matter, but the negative does. Sine we said was going to be negative. We said the cosine was going to be negative, so negative times negative is positive, times another negative makes it negative, so we're going to combine a negative number with a negative number, and we're going to end up with a negative number. So I know that the value of f double prime of 7 pi over 6 is going to be negative. Now, what does that tell us? That tells us that the graph is concave downward. And remember, the first derivative was 0 at that point, so that means we had a horizontal tangent line at 7 pi over 6. So in this understanding here, this tells us that we're going to have a relative maximum occurring at x equals 7 pi over 6. All right, now we just got to continue that process. So f double prime of, what was another one we had? We had 11 pi over 6. And what about this? Well, 11 pi over 6, let me clear off some stuff here. That's not going to clear it. Okay. Should probably pause the video, but I didn't. All right, and then going back to this picture, 11 pi over 6 is in the fourth quadrant, so it's going to be over here. I mean, it's actually closer to the x-axis, but it doesn't really matter for the purposes of our analysis. Sine is negative, cosine is positive. So let's go back up here. So that means cosine is going to be positive, minus, again, the 4 doesn't matter, so I'll put it in anyways. We said sine was negative, and cosine is positive. So positive times negative means all of this is positive. I'm going to combine it with this positive over here, and positive plus positive is going to be a positive number. So f double prime of 11 pi over 6 is going to be greater than 0, which means the graph is going to be concave upward, and that means we're going to have a relative minimum occurring at 11 pi over 6. Now, remember, the value 11 pi over 6 is not the relative minimum. That is the x-coordinate where the relative minimum occurs. We would need to plug 11 pi over 6 back into f, the original function, and calculate that value to find out what the actual relative minimum is. Okay, so I'm not doing that at the moment. I'm just trying to get the analysis to understand where there's relative max or minimum occurring, and the calculation of the value is going to be left to the student. All right, so let's keep going in this pattern. So we have f double prime of, another value we had was negative pi over 6. We could probably do this a little bit faster now because negative pi over 6 is going to be in the fourth quadrant, just like 11 pi over 6. And so we're going to get the exact same analysis here, and we're going to end up with another relative minimum happening at negative pi over 6. If I look at f double prime of negative 5 pi over 6, that is in the third quadrant, just like the 7 pi over 6 was in the third quadrant. The analysis would be the same. We're going to end up with a negative number there, which means we're going to end up with a relative maximum value occurring at x equals negative 5 pi over 6. Now, if we get into the other two critical numbers that we came across, f double prime of pi over 2, well, if we go back and calculate that, let's go back to the second derivative here. We have to look at the values, and we have to remember, hopefully we remember that cosine of pi over 2 is 0. So if I have a 0 here minus, well, cosine is in the second expression as well. When I put that, multiply all that together, I'm going to get 0 minus 0. So I just get 0 for this. Neither a positive number nor a negative number. That creates a problem when using the second derivative test, because the second derivative test fails if the second derivative is 0 at that value. So we don't get a conclusion from this. So we're going to have to actually employ the first derivative test to get a conclusion about what's happening at pi over 2. It's the same thing at negative 3 pi over 2. If you go back and calculate f double prime of negative 3 pi over 2, we do end up with 0, and so we have to go back and use the first derivative test. Now, the first derivative test, we don't need to perform the first derivative test at all the other values that we found, 7 pi over 6, 11 pi over 6, negative 5 pi over 6, negative pi over 6. We only need to do this around the values pi over 2 and negative 3 pi over 2. So I don't need to set up 7 different intervals. I just need to set up the appropriate intervals to test for these values. So let's start with the smaller of the two, negative 3 pi over 2. So I'd set up intervals from negative 2 pi to negative 3 pi over 2, because negative 2 pi was our endpoint, and then negative 3 pi over 2 was the smallest critical number next to that endpoint. And then negative 3 pi over 2 to the next critical number that we had in our list. And if you go back and look at our list of critical numbers, the one that would follow numerically after negative 3 pi over 2 is negative 5 pi over 6. I just need those two intervals to test what's happening around negative 3 pi over 2. So I need to find a value to test in f prime. Now I'm using the first derivative. So I need a value between negative 2 pi and negative 3 pi over 2. And with a little bit of thought, negative 7 pi over 4 is a value in there. There are an infinite number of others, but that's the one I'm going to choose. It's an easy one, too. Works out really nicely if you go back and look at the first derivative. Here's the first derivative at the top. If I plug in 7 pi over 4, I'm sorry, negative 7 pi over 4, that's a first quadrant value. So that means the sign of that number is going to be positive. And then, little trick here, if you remember, sine and cosine have the same exact value at pi over 4 in integer multiples of pi over 4. So negative 7 pi over 4 would also be one of those values. So for the cosine squared of x and the sine squared of x, we get the exact same value wherever quadrant we're in, because we're going to square them. And so we're going to end up with, they're each going to be a half. So we're going to get a half minus a half. So these go to 0 over here. And so I'm left with just that positive number. Whoops, went too far. So I get a positive value over here. So that was convenient in calculating this. Now, between negative 3 pi over 2 and negative 5 pi over 6, with a little bit of thought, you could find negative pi in that interval. And then if we go back to this picture so we can see what f prime is, sine of integer multiples of pi, so sine of negative pi is 0, so the first and last term are both 0. Cosine of pi, or negative pi rather, is negative 1, but we're squaring it anyway, so it's going to become positive. So we get both of these being positive. So what does the first derivative tell us is happening around negative 3 pi over 2 if both sides are both positive? Well, it tells us that there are no relative extrema happening at negative 3 pi over 2. I can barely squeeze this in here. No relative extrema, because the first derivative does not change from positive to negative or from negative to positive. It doesn't change signs, and therefore we do not have a relative extrema happening there. The last one to do would be set up similar intervals around pi over 2, and so if you go back to our values, the value right before pi over 2 would be negative pi over 6, so we go negative pi over 6 to pi over 2, and then pi over 2 to 7 pi over 6, the next value that we would have in our list numerically. And then you're going to test the values in the first from these intervals into the first derivative, and I'm going to leave that to the person watching this video so that you can get a little bit of practice without my help. You're going to find, I'll tell you the answer, they're both going to be positive again, but you should verify that for yourself. There are no relative extrema happening at pi over 2 either for this function. So all the relative extrema that were happening were back at these values as we already talked about. Now remember, those are just x coordinates. You still need to find the y coordinates by plugging those x values into the original function f to actually find the relative minimum or maximum values. I would also go to like a resource like desmos.com or some graphing utility and test out, type in this function on this interval and test out your answers. Make sure you see visually what we just determined analytically. It would just help the intuition and the understanding. All right, go study.